Welcome to another video. The topic for today is pointers. So this is actually considered one of the hardest topics in this class. The idea of pointer is very simple to understand. It's the use and the rigor, the demand on the side of the programmer from the programmer that makes them very often sources of bugs. Okay, so let's start with the easy concept. The concept of pointer. Well, a pointer is a variable. That's it. So it's a variable that contains, like any other variable, it contains a value, okay? And it just so happens that this value is going to be a memory address. So what are the consequences of having a variable p that contains a memory address? And I'm going to write down memory address using Greek letters, okay, so that we don't confuse them with just regular values like integer value, and we don't confuse them with the name of other variable. So let's say that I have a variable here called data. Data is of type, let's say, int. It contains the value 42, right? For a variable of type pointer on int to a point on data, it simply means that inside of p, I have the address at which, in memory, this variable data is located. So if the location of the variable data is a memory address that we call alpha, if I have the value alpha inside my pointer here p, then we say that p points to the variable data. So it's a variable that holds a value, but that value is a special value, a memory address, that is only used for the sake of locating another variable in memory that contains value itself. Okay, so that's the general idea of pointer. One thing that I should mention right now is you heard me say that, okay? You heard me talk about pointer variables in general, and then I said p is a pointer on int at some point. Well, yes, the data type of a variable is never just pointer. Okay, we can have a variable that is an int, we can have a variable that is a long, we can have a variable that is a double and a float. Okay, no problem. But we don't have as a data type pointer. What we have instead is pointer on, and what you would put after here is another data type, a valid data type. So you can have variables that are meant to be pointers on an int. So for example here, data is an int variable, okay? So we have a pointer here, p on int. You can have variables that are meant to be pointers on long, pointers on double, pointers on float, etc. Okay? Why does it matter? Why does it matter to know what we are pointing on? After all, a memory address is just a memory address, right? Yes, but no. So yes, a memory address is just a memory address. Let's get that out of the way, okay? But why did I say yes but no? I said yes but no because if you are trying to do anything with that pointer, and for example, the things that we would love to do with a pointer is to say, I want to read this value here by using the pointer p. Or I want to change this value here by using a notation that involves the pointer p. Okay, if we go to the extra effort of storing the memory address of a variable inside another variable, it's nice. But if we're not going to be able to interact with the content of that first variable through the pointer, it's pretty useless. So we need to be able to use pointers to read the value that is actually at the memory address they refer to, and to write at that memory address. So here's a problem. Let's say that I have D1, data 1, okay? This is an int. And I have D2, this is, for example, a double. So it's a larger variable. And it's also encoded differently, right? The way that you use 0 and 1s to encode an int value and the way you use 0 and 1s to encode a double value, a floating point value, are completely different. So I have two variables. I'm going to write down just so that we remember. This one is an int. This one is a double. Okay. All right. And now I want pointers. So I'm going to declare a pointer p1, and this is going to be a pointer on int. And P2 is going to be a pointer on double. So the first thing to realize is that when you have variables that are of type pointer on something, no matter what they're supposed to point on, they occupy the same size in memory. So for example, this would be 32-bit or 64 bits on every modern architecture, okay? This would be also 64 bits, okay? So why? Why do we have the same size? Well, because it's just like, when you write an address on an envelope. If I write on an envelope to send a letter, if I write on an envelope the address of a tiny little apartment, one-room apartment, okay? Well, it's going to occupy some space and my envelope is going to be this size. If I try to send another letter to a mansion, the house to which that letter is going to go is going to be 20 times the size of that apartment, whatever. The address still takes the same amount of space. Okay, it's written on an envelope of standard size. So what I'm trying to get at here is that a pointer on anything is a variable that has always the same size. It always contains a memory address. A memory address is going to have the same size and the same characteristic no matter where you point in memory. Okay? So those values that I have here, let's go back to our Greek letter here. So we're going to say that D1 is at address alpha in memory, and D2 is located at address beta. When I put the memory address alpha here, the memory address beta here, I need the same number of bits to store alpha or beta. But now, when I try to use P1, and I'm going to show you the syntax in a minute, but when I try to use P1 to access the data that is actually stored here, or I use P1 to change the data that is stored inside of D1, or, same thing with P2 and D2. When I try to use the pointers to access that zone of memory, well, if I try to write something, I need to know how many bytes I have available for me to write at that location in memory. So it's not enough to say, hey, I am P1, I am a pointer, I'm going to tell you go to memory address alpha, and if you want to write something there. Okay, but memory address alpha starts here, and then here's a byte, another byte, another byte, another byte, and then there are more bytes after the end of my variable. Where do I stop? How big is my variable? And even more important, or as important, I should say, if once I know that I need to write, for example, my variable on 4 bytes, okay, assuming that this is the size that I use to store an int, once I know how much memory I have at that memory address to write my data, how do I write it? How do I encode it? So you see that the type of the data that you point to is important. It's not important with respect to, what this address is going to look like, because all addresses look the same in memory, but it's important when you try to use this address to read from that location in memory or to write at that location in memory. You need to know how many bytes you're going to read, how many bytes you're going to write, and how do you interpret the bits that you are reading and writing at those memory locations. Okay? So this is why we always have a data type that is a pointer on something. You don't just declare a variable of type pointer, you declare a variable that is a pointer on something. And that's pretty much it for the concepts aspect of pointers. Okay? But we have been very vague so far. We have been saying things such as, well, I can declare a variable of type pointer on double, like P2, or pointer on int, like P1, and I can somehow get the memory address where D1 and D2 are located and put those memory addresses in P1 and P2 respectively, and then I can use P1 and P2 to either read or write the data located at those memory address. Well, all of these are things that we don't know yet how to do in the C language, right? So we need some syntax. So we are going to now move to something more concrete. So if you got the concept from this part of the video, perfect. Okay, now we're going to build on that. If the concept were a little blurry, fuzzy, because it was vague, you're somebody who prefers something concrete, then here's your chance. We are going to do things that are concrete now. We are going to write code, but as we do so, keep in mind those concepts that we just went over, and I'm going to try to draw the connection as we go anyway for you, okay? So let's start with int data1 equal 42, int data2 equal 23. We know how to do that, okay? Declaring two variables of type int. And by the way, you know the drill in those videos. Those lecture videos are meant to introduce you to the content of the module, okay? And then you have a reading assignment to go in detail. I try to use simple examples, so I tend to use a lot int. But everything that I'm telling you with int, we can also do it with, for example, double data type and stuff like that. And I'm going to, in this example, I'm going to use different data types so that we can actually illustrate different types of pointers. So we have two variables here, data1, data2. I can do a printf, data1 is %d, data2 is %lf. And I'm going to display data1, data2. So let's compile this. Let's make sure we start with a good basis, okay? gcc main.c, a.out. Okay, so data1 is 42, data2 is 23.9, and then 0000. We could get rid of that, doesn't matter, okay? All right, so now that I have those variables, first thing, how do I declare a variable that is a pointer on, let's start with the int. How do I declare a variable named p1, we're going to call it, that is a pointer on an int variable? So pointer on another variable, right, contains the address at which another variable is located. So we need to say two things, that it's a pointer and that it's a pointer on int, more specifically. So let's declare our variable like this, int star p. So the way that you read this declaration, you read it right to left. P is a pointer on, and this is how we interpret, okay? This is how we interpret the star symbol, the star operator, in the context of a declaration of a variable. Anywhere else, the star so far has been just a multiplication, right? Well, when I declare a variable, if I find a star in the declaration between the data type name and the name of the variable, that means I'm talking about a pointer. So P is a pointer on int. And here's my variable P. What does it contain? I don't know. I have not initialized it properly. So it's a convention, but it's also something that I strongly recommend that you adhere to, during this course and even after the end of this course. Every time you declare a pointer variable, assign it, initialize it to the value null. Okay, null all uppercase. This is a symbolic constant. This is a precompiler constant that is defined, I think, in stddef.h. It's pretty much what means 0 in the word of pointer. So memory address 0, memory address null. These are used as synonymous, but I really recommend you use a null constant instead. The idea is that if you don't want a pointer to point to anything meaningful in memory, well, you're going to say that that pointer points to null. It's a null pointer. These are like old terms that I used to refer to that situation, okay? So here, since I don't know yet what I'm going to do with P, I cannot assign to it a meaningful value, so by default, I assign null. And the idea is that by doing so, you make actually your code a little bit more safe to use, okay? What I mean by that is that if I don't initialize P is an uninitialized variable. What's inside an uninitialized variable in the C language? We don't know. That's the problem. There's a random assortment of zeros and one at that location in memory where P lives, and I don't know what they are. So when I try to use P, there's a chance that I'm going to try to use P to go read or write at a memory address, but that memory address is going to be garbage, random, okay? So when you try to do that in C, you generally cause your program to crash, if you're lucky. If you're lucky, you cause your program to crash, you immediately see where it crashed, and you realize, oh, I was using a pointer, but I never properly initialized that pointer variable. Easy error to find. And it's sad when your program crashing, that really is a good news. What can happen also is much more insidious. What can happen is that the variable p is not initialized, so it contains a random value. But now we are going to use that random value as a memory address. And what if that random value, by lack of luck, actually refers to a specific piece of data in my application? Well, then I think that I'm using P, for example, to access data 1, but I forgot to initialize it properly. Now I'm accessing a random part of my code, of the data of my code, and I may modify another variable when I meant to modify data 1. Or I may read the content of some memory that is inside of an array of double, interpret it as an int, and get this as a result and say, this is the value of data 1. No, it's not. So you have to be very careful about, you should be careful about any non-initialized variable, period, okay? But when it comes to pointers, the best case scenario is you're going to crash at runtime. The worst case scenario is you're going to corrupt memory somewhere in your program, and your program is not necessarily going to crash immediately. Maybe it's going to crash half an hour after the memory corruption occurred. Maybe it's never going to crash, but one of the computation that your code is doing is going to be off. And at the end of the month, when you check what your program has been doing all month long on the server side, you look at the results and you say, these do not make sense. But how do I track the moment where things starting to not make sense? That's the issue. It's better to have a bug that severely, crashes your application, so you know something is wrong, than a bug that insidiously is going to be corrupting data for like potentially a long period of time, and giving you a weird result that you cannot then trace back easily to the real cause of those weird results, right? So I know that all of this is a little vague right now, but trust me, you'll have opportunities to write bugs with pointers. That's never a problem. Everyone who learns to use pointers has plenty of opportunities to write bugs with pointers. And as you do so, I just want you to keep in mind those warnings that I give you in our first video. Okay? So going back here to our declaration, if I want to do this declaration in a safe way, I assign no, so that if I ever try to use the pointer p, okay, it's going to crash my code because it points to the memory address 0. But what I really want to do is I want to say p, I want to say points to data 1. So I'm not going to use an arrow like that, okay? But that's the idea. The idea, I want to create that arrow that I had in my diagram that says that the variable p, which is a pointer or an int, points to a variable, which is an int variable, located at a certain memory address. Well, to do that, I need to assign to p the memory address of the variable data1. So I'm introducing another operator here. The first one was a star. That didn't mean multiplication in the context of a variable declaration, but it meant we are declaring a pointer type. And then the second one is the ampersand, the same one that we use for the logical AND. And this operator is going to be used as taking the address of a variable. So we are here taking the address of variable data1 and storing it in pointer p. So if we go back to our diagram, okay, this is this part here. This part here where we said p, the pointer variable p, which is meant to contain the address of an int variable, right, is assigned the value alpha. The value alpha is the location of the variable data. So to obtain the location of the variable data, or data1 in our code actually, we use that ampersand operator, and then we assign this address, this memory address, to p. And now what we have is we have p containing the memory address of the variable data1. So we say that p points to data1. Okay. All right. Let's see if we can start visualizing all of this on the screen. So data1 is %d. Okay. I'm going to put some tabulation here to make it more readable. So I'm going to display, again, data 1 here. I'm going to display them one at a time. So the first one I want to display is the content of the int variable that we have, data 1. The second thing I want to display is I want to display the content of p. Is, oops, or else. So if I want to display the content of a pointer, I need to use the %p format specifier, okay? So %p, easy to remember, p as pointer, okay, is going to display what's inside of the variable p in an hexadecimal form, because this is a standard. When we look at memory address, we could look at them as binary number, we could look at them as a decimal number, but what we do is we look at them as hexadecimal number so that they actually give us an idea of the binary underlying representation. Okay, and I'll refer you back to a discrete structure for the conversion between binary, hexadecimal, decimal, and stuff like that. We're not going to go further in this class about those topics, but I just want you to know that what we are going to see being displayed on the screen is going to be indeed a value, an integer value, expressed in an hexadecimal base. All right, so I want to display the content of p. And then to make sure that p contains the address of data, I want to display also the address of data 1. And I'm going to display it as for what it is, a pointer, right? A memory address is a pointer value. So I use %p to display a memory address, and I want to display memory address of data 1. So I'm using this new operator here, the memory address of a variable operator, and I want to display a bunch of information. I don't need that anymore, so I'm going to remove it, okay? And I just want to focus on data 1 and its pointer right now. So let's save this, compile, run it. So data 1 is 42. Okay, nothing weird there. We're okay. P is 0x. So the 0x is a prefix that we use in C programming and many other languages, actually, like Java, etc., to indicate that we are about to write an integer value in hexadecimal base. So 0x is just a prefix that tells us what follows is an integer expressed in hexadecimal base. And so the integer value that we're talking about is 7FFD7EABCC54. So it uses the letter A to F, right? So this is definitely hexadecimal. This represents a memory address. And when we display actually the memory address at which the variable data 1 is located, you can confirm that all we did is take that memory address and assign it to P. So here we are. Pointers are variables that contain memory address. Because they contain memory address, they are going to allow us to access what is at that memory address in a different way. Okay? So let's talk about this. What can I do with my pointer? In the little diagram at the beginning, I talked about we can read, we can write memory that is at a specific address. Well, let's start by reading. What if I have the variable p, and I want to use p to actually read whatever is located in the variable data. So what's inside of data 1? An integer. So I'm going to use %d to display it, okay? And what I'm going to say is I want to display, so I'm not going to type it because that would be long. I'm just going to show you the syntax directly, okay? I want to display pretty much what is inside of data 1 when I access it using the variable p. So p, if I put p, it's just the address of data 1, okay? I need a syntax that's going to allow me to say, listen, I know p is a pointer. I know p contains a memory address. So what I want right now, what I want to compute is not what's inside of p. I don't want to get the value inside of p. I want to use the value inside of p in order to jump at the memory address that is specified inside of P by that value, and look there and tell you what is there, give you the value that is there. It's a long sentence. Huh? We call that dereferencing P. Okay? And the syntax for that, once again, is a star. So there's already 3 different meanings that we have for the star, right, in the C language. First, when it occurs in an expression, an arithmetic expression, it's just a multiplication symbol. When it occurs in a variable declaration, and more specifically when it occurs between the name of the variable and the name of a data type, it means this variable is a pointer. P is a pointer on it. Okay? And then when you use the star symbol in front of the name of a variable that happens to be a pointer, okay, or in front of an expression like that, so this is a unary operator, okay, it's not like 2 times p. 2 times p is multiplication, but if I just have star p, then it's the dereference operator. And it does what I've been telling you, like in a pretty much like long-winded way, okay? It's going to show me what's inside data 1. But it's going to show me what's inside data 1, not by accessing the variable data 1, by accessing instead the pointer that knows where to find the variable data 1. And granted, at this point, a bunch of you should be thinking, why? Why do we have this extra level of indirection? What is it doing for us? If I know that the data I want to look at is in data 1, why don't I just access it with the name data 1? Hold on, okay, a little bit more. I'm going to explain to you exactly why this matters, okay? But for now, we are looking at the syntax. We're looking at how to express, the fact that we have pointers on variable, how to use them, and then we are going to put ourselves in a scenario where it's actually practically very useful, okay? So, I want to access data 1, but I do so by saying pretty much, take the memory address inside of P, go at that memory address, and the star P expression is going to yield the value at that memory address. Let's see, save that. GCC, a.out, and we are indeed taking this memory address. We are doing an indirection, which means we are dereferencing that memory address, finding actually the data located at that memory address, which is 42, and this is what we get here. So star P, dereference a pointer P, allows me to, in terms of my diagram, okay, star P allows me to jump, follow this arrow, and find whatever is being pointed at right here, okay? All right. So I have like different things here. I have an operator that allows me to take the address of a variable. Okay, so you could say that I can go from a variable to a pointer. Okay, I go from a variable to a pointer using the ampersand operator, and I go from a pointer to a variable to the variable that it's referring to using the star operator, the dereference operator. Okay, so this address of operator and dereference operator, very, very important. Okay, last thing that I would like to point out here, a couple of things actually. Last thing to finish up on this first topic here that I would like to point out, can we have a pointer on any data type? Yes, we can. Does that include void? Yes, it does. So I can say I have a pointer ptr. Okay, that's the name of my pointer. ptr, read it right to left. ptr is a pointer on an element of data type void. So it's a memory address of something, and that something has a data type void. If I try to compile this, let's go for it. It compiles, no problem. The issue is that if I have a pointer on void, then ideally that pointer should contain the memory address of a variable of type void. Okay, let's declare void data free. I'm not going to even try to initialize it because void, the issue, as you probably guessed by now, is that it means it's a data type, that we use when a function doesn't return anything. So it's not really a proper data type. It's not a data type that is meant to store a number or store letters or store text, etc. No, it's really a data type that is meant to be a marker that means nothing. So can I declare a variable of type void like this? Well, let's double check. Compile. Well, no. Field data free, declaration as void doesn't work. So if I cannot have variables of type void, why would I be able to have pointers that are meant to point on void? Well, that's a good question. Thank you for asking it. The idea here is that what we want to do here is we want to express a generic pointer. The void here is used as a way to say, I want a pointer, but I don't know yet a pointer on what. I just want a memory address. So that means that because I don't know what kind of data this memory address corresponds to, I cannot go and read from that memory address. I cannot go and write to that memory address. So I cannot actually, use PTR with indirection here to say, for example, I want to go, let me show you real quick what I mean here. I cannot use, I cannot use here star PTR to say, hey, I want to display what's located at the memory address pointed by PTR, okay? For two reasons. One, because this is null, so I'm trying to dereference a null pointer here, that's going to be a problem. And two, because even if I pointed to a certain memory address, like I'm going to show you in a second, then that memory address, I don't know how to read or write data at that memory address because I don't have a data type, okay? So let's double check this, the two different scenarios that I just went over, okay? Try to compile dereferencing void star pointer. So it doesn't even let me go to the point where it's dereferencing something null. The compiler recognizes that PTR is a void pointer, and therefore I cannot dereference it, period. But like I was saying, even if I found a way to make the compiler accept this expression here, star PTR, then I would be dereferencing a null pointer. I would cause my program to crash. So the case of the void pointers, we're going to encounter them again later. And like I said, they're going to be used when we want to just store in a variable a memory address, but we don't know necessarily what that memory address refers to, if it's an int, a float, a double, etc., right? So it's a very special kind of use case, and it goes generally with typecasting. So the same way that we do typecasting among variables, we can do typecasting among pointers, right? So that's going to be a little bit more complex. We're going to save that topic for later. But right now, what we know is that we can declare a pointer on void. We cannot technically use the pointer on void for anything useful with respect to what we've learned to do so far with pointers. Okay, and then later we'll find a use for those void pointers, but not now. All right, so this being said, I'm going to wrap up this video by generalizing this to an arbitrary complexity level. What do I mean by that? So what I mean by that is we have a variable, so everything I did with data1 I could have done with data2, by the way, with a double pointer, okay? So we have a variable here, data1, that contains a value. I have a pointer that refers to it. Okay, let's go back to the drawing board. What if, and let me clear up some space here, okay? What if instead of having just a variable and a pointer, I add a variable, a pointer that points to that variable, and by the way, pointers are variable, right? So does that mean that we can have a pointer that points on a pointer? Absolutely. And this is going to be a delightful thing to deal with. So again, let's repeat what we were talking about here. I have the variable data. Let's say it's an int. It contains 42. I declared a pointer p1. That pointer p1 points to the variable data, which means that if data is location is alpha, memory address alpha, then I have alpha inside this pointer. And then what I'm saying is that this is a variable, so I can have a pointer on that variable, okay? The variable is of type int, so I have a pointer on int. These are the data types, okay? And this is also a variable. So that means I can have a pointer on a variable. The data type here is pointer on int, okay? Or to start using the notation, star int. And here, the data type would be pointer on int, okay? That's the data type that I'm pointing to. How do I write this down? Star int. So I could have a pointer p2 declared using this notation, star int. And p2 would also contain a memory address, okay? So let's say that this pointer p1 is a variable located at memory address beta. If I put beta here, that means that p2 points to p1, which points to data. Can I use P1 to access data? Yes. Can I use P2 to access P1? Yes. I can read and write what's inside of P1 using P2. That's what pointers do, right? They point on something, which is a variable, and they allow you to read and write the content of that variable using the pointer instead of the variable directly. But if I can read and write using P2 what's inside of P1, that means that I should be able, using P2, to also access the content of data, to read or to write it. Yes, we can do that as well. So let's talk about this. Let's go back to the code. And I'm going to say, so I'm going to change the name so that they match what we had in the diagram. I'm going to remove data2 because I have not used it. I'm going to say I have a pointer p1, which is an int star pointer. And then I'm going to say I have a pointer p2, which is going to be an int star. So how do you read that? P2 is a pointer, that's the first star, on a pointer on int. So P2 is a pointer on something like P1, because P1 is a pointer on int, right? So P1 is a int star, P2 is a int star, pointer on int star. Okay, I initialize both of them to null. I still have data here. Inside of P1, I put the address of data. Here we are. Inside of P2, I put the address of P1. Wait, can I do that? Can I use the address operator in front of a variable pointer? Of course I can. I can use the address operator in front of the name of any variable. And it tells me the location in memory, the memory address at which that variable is located. So here we are. P1 is going to point to the variable data. P2 is going to point to the variable D1. Let's do some displaying of information here. Here comes data. Here comes P1. The address of data. Why not? All right. And then I'm going to display data again by using the dereference of P1. Then I'm going to try to cover all the possible scenarios here, okay? I'm going to, after that, I'm going to say, well, I want to access P1, but I'm going to access it indirectly by P2. Okay, please. So I want to display the content of the pointer. So how do I access to read the value of P1 from the pointer P2? Star P2. Same logic than between P1 and data, right? Everything that's happening here between P1 and data, all the notation of the syntax, we can use it between P1 and P2. So if I want to see the content of P1, okay, and I don't want to use the variable P1, but I have another pointer P2 that points on P1, I can dereference P2 like this, okay? And then what? And then the cherry on the cake is, what if I want to access again data, but I don't want to access it using the data variable. I don't want to access it using the P1 variable. I want to access it using the P2 variable. How do you think this is going to work out? Star, star, P1. P2, sorry. Let me go back to the diagram real quick. If I am on P2, if I write star P2, that means dereference P2. So now I'm talking about this variable here, okay? The value is alpha. Well, if I dereference again the value alpha, then I go to that memory address and I find myself here. And this is an int, and I can display 42 on the screen like this. Let's go back. GCC a.out. So, GCC main.c, I didn't save my file. What an idiot. Okay, all right. Now that the file is saved, it's going to compile, and we can run it. So data is 42. P1 contains the memory address where the variable data is located. It's 0x7FFF. I'm just going to say the first 4 hexadecimal digits. The address of data is 0x7FFF. Okay, all right, so we are consistent. I try to access data through P2. I get the value 42. That works. I take the variable P2, I dereference P1, sorry, I dereference it. So I dereference this address 0x7FFF, etc. And I get to the variable data, and I can see its content. What if I want to see the content of P1? Well, P1 contains this address, okay? So I use P2, I dereference P2, and I find the variable P1 with the address of the variable data inside of it. If I double dereference P2, then I end up on the variable data itself. The only thing that's missing here that I didn't bother displaying is, I could probably do that right here. Up, P2. Okay, I want to show you what's inside P2. And it's going to be a memory address, so %P, and it's going to be the memory address at which the variable P1 is located. To verify this, I'm going to also printf, and I'm going to printf the address of P1. So what I did with data and P1, I'm doing with P1 and P2, okay? It's the same logic applied again between 2 different variables. One of them just so happens to be a pointer. %P, because this is an address. There we go. And I want to display the address of P1. All right, let's save. Let's make sure we save this time. Compile, run. So P1 contains this memory address, which happens to be the address of the variable data. Therefore, P1, when I dereference it, allows me to access data. P2 contains a different memory address. This is a memory address of the variable P1. When I dereference P2, it allows me to access the variable P1. You see the analogy? Okay, you see how it's the same thing repeated over, but this time between 2 variables that are one a pointer and the other one, oh, hey, a pointer as well. Okay? All right. And then what? What can we do to make this more complicated? So the goal is not to make it more complicated. The goal is to unlock your brain pretty much at this point and make you realize that, you know what? I could keep going. I could say I have here a pointer P3, okay? And let's say that this variable P2 is at location in memory gamma. If I put the address inside P3, then P3 points to P2, okay? How am I going to declare P3? I'm going to declare it as an int star 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 P3, and I'm going to set it to no initially, and then I'm going to say P3 equals the address of P2, and so on and so forth. Okay. Again, I'm always doing the same thing, again and again and again and again. It's just that I construct a chain, right? P3 points to P2, P2 points to P1, P1 points to data. If I want to, for example, display the value data, I can display it by just using the variable data. I can display it by dereferencing one time P1, or dereferencing twice P2, or dereferencing thrice P3. Okay? Once you understand that, you pretty much have in front of you the, I wouldn't say the maximum level of interaction, because technically we could go at any level of interaction, like 4, 5, 10 different interaction. But if you can understand a pointer on a variable, then a pointer on a pointer on a variable, and maybe stretch it even to a pointer to a pointer to a pointer to a variable, I would say you're in pretty good shape for this course. Okay, this is as complex as it can possibly get in this course. So this is a good, way to set your expectation here on what you need to take out of this lecture, take out of this module. And as usual, use office hours, post on Piazza, post on forum, even more so that I know that I remind you of this at the end of every video, or almost every video. But we are touching here to a very technical topic. We're just at the beginning here. We have much more to say about pointers, but you can tell already how it's kind of new, and it's going to require you to be very careful. Okay, as a matter of fact, those diagrams that I do here on a whiteboard, I really recommend that you do them on a piece of paper every time you work on pointers, so that you know exactly what's happening in memory. So you have to trade carefully, okay? You have to be careful, make slow progress, have a lot of rigor, be careful, be mindful of what you are doing in your code. And to help you get to the level where you're comfortable with pointers, it requires you to actually do a lot of practice exercise. So we're going to have some of those, of course. There's more in the textbook if you need more. But more importantly, don't just do the practice exercise on your own. Come to office hour, TAs, myself, post on Piazza, etc., for anything non-graded, and work with others so that we have a chance to see how you are working through pointers, and we have a chance to correct you just in case you are doing something wrong. Okay? All right. Well, as usual, thank you for listening and hanging around until the end, and I'll see you in the next video.